we have a rather challenging line integral question where you have to parameterize this one. Now, if you were to parameterize this, I would be doing RT as 3 cosine t and 3 sine t, where t goes from negative pi over 2 to positive pi over 2. Okay? And if you do that, it will start from here and there. Of course, to actually calculate, you have to divide by dt, multiply by dt, and these will go into these functions, and you have to multiply, so you get terms like sine squared, cosine squared, and some really hard integrals, which you don't want to do. But, however, there's a savior. What's the saving grace for this question? The fact that it's a gradient vector field. It's an exact vector field, right? So none of this is really necessary. You can just ignore that completely and use the fact that, hey, this one is a gradient vector field, and I can see that by doing the following. You can do round x, round y, 2y and 2x plus 1 minus 2y. We can compute that. That naturally makes this one hit this guy and this one hit that guy, which is exactly what we want, right? Yeah. So, So this thing here. So let me give you a new definition. If you have a vector field that looks like Mn, then this thing called perpendicular gradient of f is defined as like that. And if you look at what it does is it takes n and differentiate by x, and it takes m and differentiate by y. And this is a two-dimensional version of curl. So I'll just say curl, although curl is really a three-dimensional thing. Yeah. So this is like a curl. So when these two are the same, we say it's exact, right? So if the curl is 0, then it's going to be exact. So let's see if it's true. Now, if this hits this, what do you get? If you differentiate this by x, you get only 2, right? If you differentiate by x, you get 2. These become 0 when you differentiate by x, so you get 2. And then if this hits that, remember we're doing the determinant, if you forgot. AD minus BC. Okay, so if you do AD and then minus BC, when this hits this, of course, 2y differentiated by y gives you 2. It's indeed 0, so it's exact. Okay. Now, I'm showing you this because we will later use this for something else. So this has some deeper meaning. Yeah. Also, although you can just use the fact that differentiate this by y and differentiate this by x, and if it's equal, it's exact. You can use that, but it's actually better to just say the curl is 0. Yeah, then it's exact. Okay. All right, so that's exact. Oh, so what does that mean? That means there's a single potential function responsible for generating that as a gradient vector field, right? So let's figure that out. So there's a single function which will reveal itself first by taking 2y and integrating by x. That gives you 2xy, but you have a function of y as a possible integration constant, because we're doing partial integration, which means y is considered as a constant. Therefore, the constant could, it doesn't have to, but it could also include y. That's why instead of plus c, I'm using g of y. Then f equals to integral of 2x plus 1 minus 2y. You integrate by y. That gives you 2xy plus y minus y squared plus h of x. Okay, now how do you harmonize the two accounts? One guy says, oh, the function f has 2xy and has some function of y. I don't know exactly what it is. The other guy says, the function has 2xy, there's y minus y squared, and some function of x. I don't know what it is. Well, if you compare the two, I do see that 2xy and 2xy, they're common, so that's good. So that's definite. G of y could be both, right? Y minus y squared is a single function of y, although it's two terms, right? So g of y must be that one. And h of x could be just plus 0, right? Is that okay? Yeah. H of, like 0 could also be interpreted as a function of x as well, right? So putting both together, we have the conclusion that fxy is 2xy plus y minus y squared. And then you can put plus c to get the most generic form, but see, nowhere here it says you have to find fxy. It's just, we just figured it out, okay? Why do we like that? We like that because we have this nice formula where it says, if you have 2 points PQ, gradient of f dot dr, that's same as f, and it's like that, which means f of q minus f of p, right? So in our case, and here I'm writing PQ first. P is really something comma something, okay? It's like a pair of numbers. Okay, so in our case, what am I doing? We're doing from 0 comma negative 3 to 0 comma 3. And it's gradient of this single function, 2xy plus y minus y squared, and dot dr. Okay? And then, therefore, you just have to say 2xy plus y minus y squared, and you can plug in 0, 3, and 0, negative 3. What's that? Well, when 0 is plugged into x, that's just going to be 0, so only you get 3 minus 3 squared when you plug in 0, 3, minus, and when you plug in 0, negative 3, again, this one gives you 0, but negative 3 minus negative 3 squared. And that gives you 3 minus 9, which is negative 6. Negative 3 minus 9 is negative 12. So that gives you positive 6. That's the answer. Okay. And okay, so that gives you the answer much quicker, okay, than if we were to parameterize this and did an honest calculation. The integration becomes a lot harder. Okay, yeah. So that's a nice way.